All right, good afternoon, everybody, and welcome to today's session for SolidWorks simulation session on submodeling. So for the next 1 hour or less, we're going to look at submodeling and how you can take advantage of submodeling in SolidWorks simulation. My name is Hari Padmanabhan. I work on the product definition team at the Boston office in Waltham in the product definition team. So I write functional requirements for all the new features which go into SolidWorks and simulation. So I'm one of the members of the team. So in today's presentation, we'll talk about submodeling. We'll talk about how you used to do it before submodeling. Then I'll give you a demo inside SolidWorks, and we'll also look at some customer use cases on how they want to use submodeling in 2013. So this is a new functionality which came out in SolidWorks 2013. So it was based on the research what customers wanted. So the first thing in a high level, submodeling is taking a portion of your model. You did the analysis on the structure. It could be small or big. It's a multi-component structure. And then you identified critical regions, and you want to get more granularity of results in that region. So submodeling will help you do that without having to run the whole bigger assembly again just to get more granularity on certain regions. So we're going to use submodeling to do that. Just curious, how many of you use simulation here? Oh, great, all of you. So, okay, that's excellent. And also I want to thank the people who emailed me back on what you wanted to see. I think there are a few people who are new to simulation, so I'll try to show you some basics, maybe for 2 or 3 minutes, how you set up a simulation study, and then show you the submodeling part. So I was talking to a customer called Igor Grigic from Boucher Schroling. They're in, I think, Netherlands or in Denmark. And I was working with their consultant also who's here in the US. And I had emailed them before just to ask them what do they want to see in submodeling and how they perceive to use this. And so they sent me a document, and we were going back and forth, and I've just simplified what they're trying to do. We'll go to their example a little later in the presentation. So this is part of the truck chassis frame, just one side of it. They just showed me a simplified model where it's supported at the ends. They have some load in the middle, and that was the region they were interested in. So they did, in the traditional way today, they would do the meshing. They would get the results, they would look at the displacements, they would look at the stresses and say, okay, this is a good start, but we're not done yet. Because with simulation, you want to take the first result, but you still have to run convergence studies with the mesh to make sure your results are not diverging, you got the right result. So they went ahead and they said, okay, that's my area of interest. There are many ways to get better results. So I'm going to just mesh the whole entire assembly with a finer mesh and run the analysis. So what happened is the displacement sort of went down a little. That converged pretty nicely, but the stresses have started going up. So the user went back and said, okay, I've not got my result yet. So he does a lot of things. He can either just refine the mesh at a local region, refine the mesh for the entire model, or identify areas which are changing and identify areas which are not changing, change the mesh and do it, or you use adaptive and static analysis, which will do that for you. We'll change the mesh based on where the results are changing, and then try to refine it. So a few things you'll notice is if they used a very small mesh to get very good accurate results, and for the entire model, you'll see that the mesh has increased quite a bit from a very large mesh to a very fine mesh. There's like a unwritten rule that every time you double the mesh, it takes, I think, 2 cube or 8 times more time to run it typically that's just a ballpark number. It could depend on how your problem is set up, what is involved. So every time you start doubling your mesh, you're looking at more resources and more time. So that was one issue. And like we saw, the displacements had converged within about 2%. So that's a good thing. But the stresses were not converging, but eventually converged for this model. So with submodeling, what we're going to do is we're going to take the displacements, we just converged. We're going to see if we can reduce the mesh on the entire model and just focus on the mesh for the region you're interested in, and then converge on the stresses and get good results. So that's what we're going to try to do in this exercise. So it's just some tools to help you do that process better. Something you were already doing today is just some additional tools to do that also. So this was the area of interest for the customer. So what is submodeling? So this is the actual model they want to analyze on. This is a chassis frame, and they already identified areas in which they want to get more results. So imagine if they have to keep rerunning this entire model every time they want to look at an area or refine it, they have to run the whole thing. So with submodeling, we'll just look at one section. So this is the detail for that section. So the blue faces where it's highlighted blue is the cut boundary, which is the boundary shared between this submodel and the rest of the assembly. So that's the cut boundary. So that becomes your submodel. So this is where you would actually sort of split your model. We don't have automatic splitting tools in the tool, but if you split the model, we will transfer the displacement, complex displacement fields at that boundary to the part. So because you've sort of converged with the displacements. So that is the cut boundary. But why are you using the cut boundary? Because we have to take the displacements from those cut boundaries and apply it. So whatever interaction you have on a bigger model and the displacement of the cut boundary, we only take that to the submodel, so you don't have to rerun the bigger assembly again and just focus on the submodel. And you can refine the mesh. You can also add details provided you don't change the physics. So this is an assumption you have to make, or a judgment you have to make. And this is based on, is it really okay to do this? This is based on something called as a St. Venant's principle. Essentially what it says is if the cut boundary is far away from the area of interest and where you're interested in, then this assumption is valid. But if the cut boundary is where your area of interest is, then you cannot do this. So it's based on this theory. So you have to make the judgment call. If you're adding details inside, how badly is it going to affect the physics? So for one example, you could have it bonded. I don't know how many of you are familiar with bonded, so you just take two faces and say they are always glued together. And then you come to the submodel, so that's very fast, it runs quickly. Then you come to the submodel, and maybe you want to actually fasten these two plates with bolt connectors. So you're not changing the physics too much here, but you're adding a little more details. So you can't just say you come to the submodel and leave it free so that it starts moving out. That assumption won't work. So you have to make that judgment when you do that. So this is the example where this area of interest is far away from the boundary, so this assumption was okay. So what we're going to do in this demo today is we're going to look at something similar, where we're going to look at the chassis frame, and we're just going to, we know the higher stress regions or critical regions are here, so we're just going to create a submodel analysis for this region and focus on this part. So we'll do the first set of analysis on this. This is another example for a pick-and-place machine. This was the motor chassis, and they were trying to just do the rough analysis on the larger model and do a smaller analysis. So with that, I'm going to, before I go to SolidWorks to show you the steps to set this up, is there anything specific people want to see or any questions before I go, or if I'm going too fast, or it's clear? Okay, right. So I will answer questions, and as I set this up, I'll give you a little more details on where it works, where it does not work, what analysis you can do, what you can do inside the submodel. I'll add all those details as I go through these examples. So this is a frame you've already built. You can do it as solids. It does work for solids. In this case, because it was a box frame type of frame, I'm just using the outer surfaces, and I'll just give a thickness to these surfaces in simulation. And I will also point out some new functionality in 2013 as I'm setting the submodeling analysis. So I'll just take a few minutes to review analysis. For people who have not used analysis, you always start with a study, which will tell you, okay, you want to give what type of study it is. Submodeling is supported for both static analysis and nonlinear static. So you can go from a static analysis as a parent model or the larger model and continue as a static analysis with a submodel. You can also do the same thing with nonlinear static and then finish it with a smaller nonlinear static model. You cannot right now go from a static model for a larger model and do the nonlinear analysis on a smaller model or a submodel. There's only one customer, which I'll discuss later, who wanted to do that because he wanted to add more realism to the plastic material in the submodel, and that's why he wanted to do that. Is there anybody here who would benefit from that feature? I'm just curious. Okay. So I already have that static study set up. It lists all the surfaces. It gets the material from SolidWorks, or you can go ahead and get the material from, you can add the material here yourself with apply edit material. So you can do it either way. I've already assigned all the different thicknesses to the shell. So if you edit any shell, you would see that the thickness is being applied. Now, by default, we consider the global bonded. So these are the different surfaces. If they are touching, it'll try to connect them through a bonding algorithm. I'm just going to fix the ends with this fixed joint, and then I've applied various forces on these faces in the model. So I'm going to mesh it. There's some new functionality in 2013. Previously, if you look at the mesh, it'll just give you a mesh on the surface. In 2013, you can render it with 3D. So you know the thickness you provided, which way it's getting extruded. So if you don't like it, you can go back to the definition and you can flip it if it's not matching the actual geometry you think it should match. So this is something new in 2013, where it will show you the thickness. And we have taken this to the results as well, so you can just get the results at both the top face and the bottom face as well. So I've already run the simulation, so I'm going to look at the displacements. This is where I'm seeing the maximum displacement. And I can look at the stresses, where I see most of the stresses in this area. So again, I can right-click I can edit the plot and render it using 3D as well. So you'll get the plot with the thickness included. And one nice functionality in 2013 is you can get a result only on selected faces. If you're only interested in, say, this area, I can edit a plot, and I'll remove the render thickness, I can say show plots only on selected surfaces or bodies. In this case, it's only surfaces. I can just select faces on which I want to just see the result. And it'll just create that plot for you, so you don't have to go back to SolidWorks, hide it, show it, then come back, because all plots have now those faces are hidden, so you can tailor it specific to a plot. And then you can also have the result. If you double click on the legend, you can say show the min and max only on things you have shown on the screen. So you can sort of compare your parent and submodel and see the differences. So you can do that as well. So I'm just going to say automatic. So it'll try to, this is where the high stresses are, it'll try to base it based on that. So we'll assume that the after test with the displacements have converged. So I'm going to do a little more detailed analysis. And if you look at the mesh, I have used I wouldn't say quite a fine mesh, but it's coarse. But for displacements, I'm okay with this result. So to continue from here to a submodel, you can right-click on the study and select Create Submodeling Study. So the submodeling study will become a child of this parent study. So I'm just going to take submodeling. We just want to give you the advantages, and there are some limitations. And this is a big list, don't be scared about it, but I'm going to show you, I'll tell you the limitations as we work through this example. So the first thing it asks you is to select the bodies you want to include in the submodel. So I'm just going to include these faces in the submodel. So which means this becomes now my cut boundary. So the first limitation I'm going to bring up here is right now the boundary has to be cannot be merged in respect to mesh. So when I say merged, if you take two faces and they're touching, when it meshes it, if you do a compatible mesh bonding, it will try to align all the mesh from both faces where it's touching, and it'll do a merge of all the nodes. So you have only one node, but it's a common area because it's a common area. We can't do a cut for submodeling on that. So it has to be an incompatible mesh. So if you have two shell edges touching and you make it compatible, you won't be able to cut it there for transferring the loads. So in this case, it's an edge on a face, so it doesn't automatically merge it. So you can use that as a cut boundary. So I'm just going to select OK. It's going to take a few minutes, not few minutes, but it's going to take some time because it's going to create a derived configuration. Later in the second example, I'll show you the benefits of using derived configuration, is because you can add or delete geometry within the submodel without affecting the parent and invalidating those results. So we'll talk about that in the second example. So it has to go back to the parent, create the derived configuration for this, and come back. So if you go to the configuration manager, you would see that now the submodel is under derived, so it'll leave the parent alone and not disturb it. So whatever changes you make in the submodel won't affect the parent and the results. So it's a one-way. So if you're making any changes in the parent, it is going to affect the submodel. So it'll always check if the parent is up to date before running the submodel. But the changes in the submodel will not affect the parent. So what it does is it creates the surfaces you included, and it'll exclude all the other surfaces from the parent. You always have the option to include it back later. Then the cut boundary moves to a different location. The only limitation here is you can't include, the submodel cannot include all the parts of the parent. Then there's no benefit of doing submodel. And it will, if any contacts are defined for these parts, it will bring it in. So this was the only global contact defined at the parent level for these parts. So it brought that in. And it will add a new item to show you where it transferred the loads, the displacement fields, from what's the common edge of phase between the parent and the submodel. So just going to bring one feature here which will contain all that information to pass on to the solver. So which will be these edges. And if there are any forces applied inside the submodel, it'll bring that in as well. You cannot change it, that's why it's grayed out, but at least you can review it to make sure you have the correct. You cannot add any new features, you have to do it at the parent level, new forces, but you can add new connections and new connectors. So we will talk about this in the second example. So you can refine a few things. And obviously you can refine the mesh as well. You can make it finer. If you just run it just as is, it will just take whatever setting you had at the parent, use the same settings for the submodel for mesh and everything else. So you're going to get very similar results. So if you look at the mesh, it's going to be very coarse. But you can go back here and you can apply mesh controls on areas of interest. And I'm just going to go ahead and say OK, and mesh it back again. So while doing this, you don't have to see it's running much faster than your parent model because it doesn't have to run the whole model again. It's already got the displacement field at the boundary, so it's just going to focus on this model and just running this. So you've got more freedom to try a lot more things. But if you change anything in the parent, it will flag it here in the submodel, and you'll have to run it again. So if you go back to the parent, it'll tell you under the tree which submodel it's referencing. So you know which submodel it's going to affect. So this is the background for submodeling. We'll go over one more example for submodeling as well, where we'll add details and make changes. And then we'll discuss a couple more customer use cases. So any questions so far before we go? Yes?
How sensitive is to the mesh at the boundary of this when you run the master model?
Right.
How sensitive is it to the coarseness or fineness of the mesh at the boundary?
All right, that's a good question. So at the because the boundary is not the region of interest and it's far off from the region of interest, the good practice is to not change the mesh on the boundary too much. Try to keep it as close as possible to the parent. But having said that, we do interpolate the mesh correctly from displacement fields to whatever mesh you have. So you can still use a finer mesh, but don't keep that as your focus of changing. Any other questions? All right. So one of the textbook cases for submodeling we haven't completely solved it, is if you look at the literature, it'll be like taking a beam model. How many of you here use beams or are aware of beams? A few of them. So if you take a beam, you expect the cross section to be uniform along. You have tapered beams as well, but so when we analyze it in simulation, to analyze it quickly, we can simplify it as a 1D line element and give the cross section of the beam instead of doing it as a 3D. Yeah, if you have bolts and nuts and holes and you want all that to be incorporated, you have to either do it as a shell or solid. But if you don't have that, you make it a beam. So people like truss structures and frames, they would just draw sections and just analyze that without the details and make judgments based on that. So submodeling, if you look at literature, will say, okay, take the beam model, very coarse line model, and I'll identify an area, and then I will actually build the joint details in the submodel. So that was a textbook case Because of our compatibility mesh, so you'll see that in one of the line items in the limitations, we cannot, when you use a beam mesh, it merges and all the nodes to make it one. So at this stage, we haven't supported that yet. So that's going to be a limitation, but I'm going to show you a workaround for that. So how many of you think that's a big limitation for submodeling and we need to fix it because it's just collecting data for where you want to start off with a very coarse beam mesh, then do a submodel on specific joints. Anybody in the civil construction? Okay, all right, that's good to know. So what I have here is just a simple structure. You can have a big building. It's just a frame, but I've separated out the section here because I have a detailed joint connection at this place, which I'm going to introduce in the submodel and not at the parent level. So I'm going to create a much coarser model and make my judgment saying, okay, displacements are pretty close to what it is, and then apply my new joints to see if the joint will hold those displacements. So I have this. So the trick here is because we cannot cut a beam and beam between the parent and submodel, I introduce like a incompatibility here. So I have a small band which I'll make a solid. So the key here is you have to run the complete beam model and this model to make sure that displacement patterns are very similar. With a small beam, it is okay in this model. So you can make the same assumption. So this is almost like it's a cheat sheet to say, okay, now transfer the displacement fields on the solid. Then in the submodel, I'll connect the details to that small solid because it transferred all the displacements. So let me just show you the mesh. So you'll see that this is a 3D representation of the beam. If you've not been using the 3D representation, it'll look like these cylinders, the 1D element. And then these are the solids I created just to transfer the load, because if these two are beams and gets merged, we cannot cut it for the submodel. So I've just introduced like a solid element here, but inside this is all beams, because this closely represents the connection I have. I'm just going to include the details in the submodel. So I just have a parabolic load here, and if I create the displacements, so I'm just going to animate it. You'll see that it's behaving this way. It's just bending. So I'm just going to create a new plot. Just look at the displacements. I think this doesn't update. Yeah, so it's about 1.221, just to compare the submodel and the parent model. So this is the parent model. So this is the region I'm going to analyze, and I'm going to take this region and add all the details in my submodel. So I'm going to do the same thing. I'm going to say create submodeling study, and this is where you would see that you cannot use it for the beam and shells. I think more details in the submodel by connectors and pins. So there's a few limitations like that. So I'm just going to, I don't need the internal geometry because I'm just going to replace it with more details. You can take it, you can use the existing geometry and just make hole cutouts or add more details, or you can just replace it with new geometry inside without changing the physics. I'm just transferring the displacement fields here. So it's going to give me a new study with just those 4 components, and it's going to exclude everything else. So this is where what I'm going to do is, in that part which was the structure here, I'm just going to add the holes and replace those 3 bodies with the actual details. So I'm going to suppress this guy, which is the 3 bodies. So I'm going to come back to the submodel and just update it to make sure everything was updated. And you'll see that now I've added the plates. You can have fasteners, but I'm going to replace it with bolt connectors inside simulation. It has the gusset, it has the plates, which again are bolted. Right now I'm going to run 2 studies, one with just the bonded. So everything gets connected to the boundary nicely. And I'm just going to come back here and make everything solid because I don't have to analyze the whole model, so I can go fine. You can add things like these ribs in the side, the plates, which you cannot do at the beam level. It got the materials what you had already applied in SolidWorks, and it brought in all the displacements on these faces from the parent model. So well, I can go ahead and mesh it and just run this model with all these details without having to run the parent after I've transferred all the loads. And so again, you have to be careful. Yes, there's a stiffness change between the parent and submodel, but that's based on your engineering gut feel. Yes, this is not changing it too much. You can't go from almost like plastic to rubber or something like that, which will change the physics completely, which means it's going to affect the parent. So the displacements are pretty close, and you can see the stresses as well on where it's going to affect it. Basically here, so if you have a lot of bolts and welds here, it is going to take the load based on that, what you had given. So this is how you would add details, and every time you want to make a change, maybe from these 4 holes, you want to just go with 2, you can test those here without having to affect the parent. That way you get a little more flexibility on using this functionality. So the other thing I can do also is like I can go to, I can just duplicate the study and just create, instead of having all this rigidly bonded, I can give a contact, no penetration contacts, allow it to slide and add the bolt connectors if you want to, or add a little more interaction inside to the model as well. So here I could come back and go to contact set and add not this face, and something small, select another. In 2013 is now you can press the right mouse button to tab through these, which you were not able to do. You had to keep coming back here, selecting this and doing it, and then you can finish it. And then I can go ahead and add the bolt connectors as well. Again, add, tab, and then I'll just pin this so all the settings are stored. I'll just use an axial load. 400 Newton. And let's add it here. I didn't use the tab. That was done. Oh, that was in the back. All right, so I'm done with those 4. I'm just going to test it with this. Maybe I need more, and I go ahead and run it. So you're still making only changes here and not affecting the parent as well. You could also change the bolt. I'm using a hole wizard, so instead of these 12, I can make it 6 or 8 and check it as well without having to affect the parent. So any questions before I go to the next? Yes?
What's your favorite way of handling wells? Those are welded.
Wells? That's a good question. So what's the best way of handling wells? You can use submodel. You can add the wells just in the submodel, and then you would have the load path go through the wells rather than the plate. So if it's bonded between the two plate faces, you'll make it free, but bond the wells on both sides. Yeah, so there is a limitation right now, is that you can create these new cosmetic well beads in SolidWorks, but when you come to simulation, they mean nothing. They don't come as solids. At least in the old workflow, you were actually creating a geometry which would work in simulation. In the new workflow, it doesn't. So we haven't fixed that. So it's still painful. You have to do an extrude, or you have to do the weld. You have to build the weld. So how many of you think we need to support that as well? Wow. Okay, that's a good thing. Thank you. Okay, so I'll add it in the next release plan. Because that's quite a bit. So right now, the only way is to model it. And then what you can do is in the parent study, go ahead and exclude them. So it'll come under excluded parts. And then you can come here and include them. Yes?
Just to make sure I understand. So when you did your submodel and added the additional braces and
Right.
facets, you went back to the model and unsuppressed them?
Yeah, I unsuppressed them in the SolidWorks tree, yeah.
For just the derived config?
Yeah, only for the derived configuration. So yeah, so I'll just show you that. If I go back to the submodel, it'll remove those.
Okay.
Yeah, that's why we use configurations. That's what I did. Yes.
Oh, you did? Okay.
Yeah.
Sorry.
That's what I duplicated. Yeah. Yes, you can. Any other questions? Yes. This is an assembly, yes. It can be done in both. Yeah, this is an assembly. It can be done both in part and assembly. Yeah. Now here it says steel brace part, but if I go up, it'll say toolbox assembly. Oh, you mean you can unsuppress an assembly? Yes.
The whole thing can be done in
assembly, yeah.
It says submodel.
Right. So yeah, okay. Now it can be done on the assembly, yeah. So any other questions? Yeah.
So when you do submodeling, you don't have to redefine your load.
No,
Your load is still the same.
right. Because if you redefine the loads of the submodel, you're changing the physics, which means that effect is not taken into account in the parent. So we said we are going to allow you to add it here. We can only add contacts and connectors, assuming that you'll use it wisely. But again, with simulation, it's what your assumptions give you the right results, right? So, yeah.
You need to make sure that your displacement at least converges on the master model before you start running it.
Yes, that's something you'll have to do. There's no tools here because of submodeling to help you do that. That again is left to the engineer to still do that. So you'll have to run a few parent models, and also you might know from experience that it can go beyond this. You might have hand calculations to give you a ballpark. Yeah, you still have to do that. Have any question? No. So this is the model with the contacts and displacements on the fields, and the stresses based on that as well, where the bolts are taking a lot of load compared to the others. So I'm going to go back. So just to recap, this is an assembly. So this is an assembly, so you can have sub-assemblies here and include that as well. And it does make derived configurations. So if I go back to my parent model, which means if I go back to my parent study, you will see that I don't have any of these details because I only unsuppress them in the derived configuration. Yes? Sorry, I didn't, let me come back. These are multi-body parts, yeah. Yes. So you can unsuppress and suppress bodies as well, yes. Yeah. Yeah, it creates a derived configuration. Because even though you have a part or as an assembly or multi-body parts, when it comes to simulation, it just uses just the bodies. I think it's SolidWorks Simulation Professional, I think. Professional. Yeah. So just to recap some few things we talked about, it's available for the static and nonlinear statics. At the cut boundary, it has to be incompatible. Available for solid shell interfaces. Also, we looked at a case where it's available for beams. You cannot cut a beam though. So it can be inside or it can be outside, but it can't be at the boundary. And also make sure it's away from the area of interest. It works in a derived configuration, so you can make some geometry changes and add connectors and contact. So these were a couple more customers I was working with when I was doing the research for this functionality. So this was from Cobham. They were looking at an antenna plate. They had a rougher model of the back plate. But then once they cut it in the submodel, they wanted to add all these details and do a more finer analysis on this. So today what they do is they estimate what the displacements and forces will be on the body, and then they try to add that in. So this was one example of a customer. The other one was Richard Pitts from Great Western Manufacturing. They had the sifter machine, which actually shakes on these two bearings. So that's the joint where this blue plate and comes here. There's some joints here which they want to analyze and look at different ways, because the bearing comes here, look at various ways to join it or try different joints and do a submodel analysis on this as well. So this was another use case where they can use submodeling so that they can do that. Ideally, they want actually to transfer from a dynamic analysis, do a submodeling and dynamic. Today, it's not supported. But at least he says, I know where at what case they have the maximum load, so I can just do it for that. Is there anywhere here, anybody interested? It's a harder problem to solve, but I'm just curious, is anybody interested? One, okay, good. What type of application would you, or I'll contact you later and get that, okay? So just to wrap up, so there are some advantages of using submodeling. You can try to get more accurate results at the area of interest. You can experiment with different designs, and also make sure your mesh refinements are enough to get accurate results. So the presentation is available. It's been recorded. So I think around March 1st week, they'll post it on the customer portal with all the SolidWorks World presentations, so you can get it. We always do customer visits, so if any of you is interested, we'll come there, find out how you're using software. And this is also a good time to give us input on what we should do for the next release, because we're building up our master list. And enjoy the rest of SolidWorks World. Thank you.